Glad that started. Good morning, everybody. Welcome back to Abstract Algebra. Plan for today is we're going to continue our regularly scheduled programming. Talk some more about normal subgroups. Got my usual office hours this afternoon at 2, tomorrow morning at 10, tomorrow afternoon at 1:30. And as far as homework goes, you got nothing to do for a week still, but I'm going to start taking a look at homework 6, which will be due next Wednesday. And as a reminder, for homework 6, you are allowed to work in groups and have group submissions of just one group for up to 3 students, which means you just want to have a group of 3 students and you just want to write up your homework 6 together and submit. I'm okay with that. Just, if you're working together, wear a mask and be safe and all that. Any questions or comments before we get started for today? So, group of mathematicians and a group of engineers traveling to a conference. So they go on a train. The engineers all purchase a train ticket, but the mathematician group only purchases 1 ticket for the whole grade. Engineers are all razzing the mathematicians like, "Wow, you're going to get in such trouble. Why would you do that?" And then all of a sudden, one of the mathematicians shouts out, "Hey, the conductor's coming!" All the mathematicians immediately climb into a single restroom on the train. Conductor goes, checks each of the engineer's tickets, knocks on the restroom door and says, "Hey, I need your ticket." One of the mathematicians passes out that 1 ticket. Conductor checks it, thanks them, goes on their way. Mathematicians got by. Engineers are very impressed by this. So, a couple days later, their same groups are returning by train, and the engineers think, we're just as good as the mathematicians are. We're just going to buy 1 ticket as well. So all the engineers buy just a single ticket for the group. Mathematicians don't buy any tickets at all. So they get on the train. Engineers are looked at the mathematicians like, "Wait, what? Not even 1 ticket? How are you going to get away this time?" And one of the mathematicians says, "Hey, the conductor's coming." All the engineers immediately pile into a restroom. Then one of the mathematicians knocks on the restroom door and says, "Ticket, please." I swear, a good chunk of my joke book is just making fun of engineers and physicists. And other people who do math but don't call themselves mathematicians. Alright, so it's been a few days. We haven't really talked about this stuff since Friday, since Monday was plain set. But you may recall we talked about how to define a quotient group last Friday. We said that if H is a normal subgroup of G, then we could take G mod H as a quotient group whose elements are just going to be the left cosets of H. Elements of the form little g times H, where little g is just something from the group. And we said that actually forms a group under the operation. If you have 2 left cosets, AH and BH, you can multiply them together to just get A times B H. The left coset you would get from taking A times B within your group G. Whoa, what does that mean? Anybody remember what it means to say that H is a normal subgroup of G? Yes, Selene?
Little g, H, G inverse is in H.
Whoa.
No.
That is an equivalent condition. That's not the definition, but we did prove a theorem that says that is logically equivalent to saying H is a normal subgroup of G. The definition is just that little g times H equals H times little g for all little g integers. But what you said it would work as well. So in other words, H is a normal subgroup of G if all of H's left cosets and right cosets are equal to each other. And what we were doing last time is we wanted to show if H is a normal subgroup of G, then G mod H does form a group. And so we checked the usual, we rounded up all the usual suspects and checked them to see when does this form a group. And we checked that closure checked out, associativity checked out, the fact that this group had closure and associativity mainly just boiled down to the fact that the original group G has to have closure and associativity. We showed that G mod H always has to have an identity element. What was the identity element in this quotient group? What did we say was the identity element? A coset that if you multiply by any other coset, you would just get back that other coset. Okay?
EH or just H?
Yeah, exactly. So you have an identity element that's just H itself, or the identity times H. Since AH times EH is equal to AH, which is equal to EH times AH, for all an element in our group G. So we have an identity element. That checks out. We also had inverses. In general, what did we say was going to be the inverse of the left coset AH? In other words, which left coset would you need to multiply AH by that'll get you to EH? Peter?
Wasn't that A inverse H?
Yeah, that's exactly it. You just take A inverse and multiply by H. Since for all A and G, if you took AH and multiplied by A inverse H, you would happen to get the identity if you multiplied in either order. So closure checked out, associativity checked out, identity checked out, inverses checked out. We got all the usual properties you need to show you have a group, but none of those required any knowledge that H was a normal subgroup. And so the question still remained last Friday, how did we, why did we need that H is a normal subgroup of G? I'm going to do something I normally don't do. We're going to flip the page early and then come back to the page where it says, why is it necessary that H is a normal subgroup of G? No, we're going to flip to the page that says that. And I want to show you an example that shows what exactly goes wrong if your H is not a normal subgroup of G. So this is going to be on the page that says, why is it necessary that H has to be a normal subgroup of G in order for this to work? Let's look at an example. I'll look at the group G being equal to S4 and the subgroup H. There's going to be the subgroup generated by 1, 2, the 2 cycle. It's been a week, so you may not remember this, but we actually showed on the front page of this packet H is not a normal subgroup of G. Since, for instance, if we were to take, multiply this H on the left by the 2 cycle 1, 3, we do not get the same thing as if we take everything in H and multiply on the right by 1, 3. So H was a subgroup of G, but not a normal subgroup. And we're going to show what goes wrong if we try and take G, the quotient group G mod H, where H is not a normal subgroup. So I'm going to look at a couple cosets. If we were to take this coset, 1, 2, subgroup generated by 1, 2, and multiply on the left by 1, 3, which is the same as just taking everything in the set containing the identity element and 1, 2, and we multiply everything on there on the left by 2 cycle 1, 3. What are we going to get in there? 1, 3 times the identity element is just going to give us 1, 3. What would we get if we took the 2 cycle 1, 3 and multiplied by the 2 cycle 1, 2? Well, 1's going to map to 2, which maps to itself, so 1 will map to 2. 2 will map to 1, which will map to 3, so 2 maps to 3 overall. 3 maps to itself, which maps to 1. 3 maps back to 1. This is the left coset we're going to get. We're going to get the 2 cycle 1, 3 and the 3 cycle a 1, 2, 3. Which, by the way, I'm going to write this out as 1, 3 times h. Which, by the way, will happen to give us the same thing as taking 1, 2, 3 and multiplying by h. So we have the same coset that can be represented in 2 different ways. We can multiply h on the left by 1, 3, or we can multiply h on the left by 1, 2, 3, and we'll come out to the same thing. On the other hand, we could also take 2, 3 times h, which will give us 2, 3 times all the elements in the set, identity 1, 2. Which if we multiply out, will give us 2, 3, and 2, 3 times 1, 2. What would we get if we multiplied the 2, 2 cycles together? 2, 3 times 1, 2. This time I'm not going to do it for you. Someone's going to have to do this for me. Well, first of all, what would 1 have to map to if we multiply these 2 cycles together? 3. 1 maps to 2, 2 maps to 3, so I think 1 has to map to 3. Lauren, what would 3 have to map to?
2.
Let's see, 3 maps to itself, 3 maps to 2. And then 2 maps to 1, which maps back to itself, so 2 is going to map to 1. That's going to give us this set, 2, 3, and 1, 3, 2, which is going to be equal to 1, 3, 2 times the coset h. So what do we have? We have shown that if we take 1, 3 times h, we're going to get the same thing as 1, 2, 3 times h. And we've also shown that if we take 2, 3 times h, we're going to get the same thing as 1, 3, 2 times h. Went through this a little bit quickly, but just want to stop and make sure, see if anyone wants me to slow down or go back over any of this. Everyone okay with this so far? So these 2 cosets are equal. These 2 cosets are equal. So if we were to multiply these 2 cosets together, we should then get the same thing as if we were to multiply these 2 together, right? If these are equal and these are equal, if we take this times that, we should get the same thing as that one times that. Makes sense. Basically saying something along the lines of if A is equal to B, and if C is equal to D, then AC should be equal to BD, right? All right, let's check to make sure that happens. So if we take 1, 3h and multiply by 2, 3 times h, by definition, that's going to give us 1, 3, 2, 3 times h. Which, if we multiply 1, 3 times 2, 3, h here, again, just being the set containing the identity and the 2 cycle 1, 2. What are we going to get if we take 1, 3 times 2, 3? Well, first of all, what's 1 going to map to if we multiply these 2 cycles together? That's 1. 1 maps to itself, 1 maps to 3. What's 3 going to map to? Okay. 3 maps to 2, 2 maps to itself. I think it's going to map to 2, and then 2 will map back to 1. It's going to give us 1, 3, 2 times h again. Oh, hey, it's going to give us this thing, which is going to be made up of, what did we say over here? 2, 3, and 1, 3, 2. So since since these multiply to 132H, it should get the same thing as if we multiplied these two together, right? 123 times H, 132 times H. If we multiply these together, we're going to get 123 times 132 times H. What would we get if we multiplied the 3 cycle 123 by the 3 cycle 132? Keeping in mind that these elements are inverses of each other.
You just got the identity.
We are going to get the identity. This is going to give us the identity times H, which will be made up of the identity in 1, 2. So when we took these two cosets, we said A equals B and C equals D. We multiplied A times C together, and we got the same thing as we got when we multiplied B times D together. Elaine?
We did not get that.
Oh my goodness gracious. That's why you need a normal subgroup. Nothing to do with closure or identity or inverses or which one am I forgetting? Associativity. It turns out to be the case that multiplication is not well defined if you don't have a normal subgroup. So we've shown if H is a subgroup but not a normal subgroup of G, it's possible to have that A1H equals A2H and B1H is equal to B2H, but A1H times B1H is not equal to the same thing as A2H times B2H. That's weird. So that tells us, so another way to say this is to say our multiplication operation is not well defined. Yes, Nick?
So does that mean it's not a group, or does it just mean that
It's not a group. It's not a binary operation. Like this operation here just does not make sense if H is not a normal subgroup of G. Because it's possible to take the same two cosets, write them in different ways, and suddenly the product of these two things is not equal to something that should clearly be equal to it. So what happens is, if H is not a normal subgroup of G, you're going to end up in a situation where this sort of thing occurs, and that leads to lots of sadness and tears, because then two things are not equal to each other that very much should be equal to each other. And it turns out, if H is a normal subgroup of G, this can't happen, which is what we're going to be proving next. So just because we have closure, associativity, identity, and inverses, all of that is meaningless if our group operation doesn't make sense. Which, really, that's what we're saying when we do this, is our group operation where we take two cosets and multiply them together by just taking the two elements and multiplying that coset is not well defined. For cases where H is not a normal subgroup, you can have things where A is equal to, or A1 is equal to A2, B1 is equal to B2, but A1 times B1 is not equal to A2 times B2. Which is not something that you want to have happening in your group structure. Doing this would be basically like saying you could multiply two cosets together, the same two cosets, and yet end up with two different products. It's like saying, hey, I could take 1 3H times 2 3H, and I happen to get this, but I also happen to get this. I'm multiplying the same two cosets together, and yet somehow I'm arriving at different answers each time. And that is no bueno. We take two cosets, no matter how we multiply them together, we always want to get the same result every time. And yet, we found a case where multiplying these two cosets together, one way gives us this, but we swap out the way in which we write our cosets, which should be fine because this is equal to that, and this is equal to that. But once we rewrite the same cosets in a slightly different looking way, our product doesn't end up being the same. And that's why we don't get a group out of it. Yeah, questions or comments about what's going on here? This is pretty weird. It's the first time we've ever, in this class, we've seen something like this occur. In that case, let's actually prove that if H is a normal subgroup of G, then this can't happen. So I'm going to flip back the page to, let's prove if H is a normal subgroup of G, then G mod H forms a group. And now we're going to prove that if H is a normal subgroup of G, because remember, in this example we looked at, H was not a normal subgroup of G. We're going to prove if H is a normal subgroup, this sort of shenanigans is not going to happen. So here's what we're going to prove. We're going to prove that if H is a normal subgroup of G, our group operation is well defined. In other words, if A1H is equal to A2H and B1H equals B2H, then the product A1H times B1H should give us exactly the same thing as the product A2H, B2H. i.e. that A1B1 times H has to be equal to A2B2 times H. This is going to be what we're going to prove. We're going to show that if we have a normal subgroup, then no matter how you write your left cosets, we could write the same left coset in two ways for A1 versus A2H. We could also write the other left coset in two different ways, B1H versus B2H. And we're going to say if the two A cosets are really the same thing, and if the two B cosets are really the same thing, then if we take the A coset times the B coset in either order, we're always going to arrive at the exact same result. You all ready? Hold on to your hats, because this proof is going to have lots of hats in it, as it turns out. So here's our proof. So I'm going to start off by saying that if A1H is equal to A2H, I'm going to use a property of cosets that says A1 has to be an element in A1 times H. Because if H is a subgroup, H has to have the identity. So A1 we could always write as A1 times the identity, which will give us an element in A1 times H. But we're assuming that A1H is equal to A2 times H. So if A1 is an element in this left coset, A2 times H, what does that tell us about a way that we could write out A1? What would be the form that A1 would have to take in order to be in this left coset? Nick, what are you grinning at right there?
I was gonna say we could do like A2 hat or something like that.
Don't be ridiculous. All right, I'm going to answer this question because Nick has disgusted me. A1 has to be equal to A2 times some little h or some little h in big H. Because that's what elements in this coset look like. If A1 is an element in this coset, that means A1 has to be equal to A2 times some little h. And we can also say, similarly, since B1H is equal to B2H, then since B1 is an element in the left coset B1H, which is equal to B2H, then B1 should also be equal to B2 times little h, right? Right?
Little h hat.
Why little h hat? Why doesn't that have to? Why?
But it's not necessarily going to be the same element as another one. Yeah.
Indeed. Yeah. What did I call this one? This one I just called h prime. Hats are coming though, don't worry.
Great.
For some little h prime. So in other words, B1 being in the left coset B2H means B1 has to be equal to B2 times some element in the subgroup H by definition. But it doesn't have to be equal to B2 times the same element in H as A1 is equal to A2 times H. A1 has to be equal to A2 times something in H. B1 has to be equal to B2 times something in H. But it doesn't have to be the same thing in H. So this one I'm just going to call little h. This one I'm going to call little h prime. So far, so good? So now, I need to take an arbitrary element in one of these super left cosets. We're going to show, we want to show, I should say, that these two cosets are equal, right? A1, B1 times H is equal to little a2, little b2 times H. And to do that, we're just going to do your typical subset argument, show that every element in the first set is contained in the second, and vice versa. So we can say, for any element in this left coset, little a1 times little b1 times H. By the way, what would an arbitrary element in that coset have to look like? Guess Elaine.
A1, B1, H hat.
Really? You don't want to use H or H prime?
No,
Why not?
because they're something different.
Because they could be different. So now I need another arbitrary element in H, which may be very different from the H, little h over there, or from the H prime down there. So this time I'm going to come up with a third element in H, call it H hat. And our goal is going to be to show this element has to be an element in this thing. Meaning we'd like to show that this element can be written in the form A2 times B2 times some element in H. Let's see if we can do that. A1, B1, H hat, I claim is going to be equal to A2 times little h, because A1 is equal to A2 times little h, times B2 times H prime, times H hat. So here, I'm just using our alternate forms of writing A1 and B1 that we found over here. A1 is equal to little a2 times h. B1 is equal to B2 times H prime. So if we take A1, B1, H hat, we're going to get A2, H, B2, H prime, H hat. What we would like to do is we'd like to say that this is of the form A2 times B2 times something in H. The problem is we can't do that from here because we have A2 times something in H times B2 times something in H times something in H. A lot of elements in H coming up here. So here, in fact, we can't show, in general, something of this form has to be able to be written in this form. Unless we use the fact that H is a normal subgroup. And if we use that, what we can say, I'm going to split up this HB2 off by itself with some power of associativity going on. I claim that since we know that H is a normal subgroup of G, that's going to tell us that little b2 times big H has to be equal to H times little b2. That's by definition of H being a normal subgroup. Because if we multiply something by H by something on the left, we should get the same thing as if we take H times something on the right. And here we have some element in this set, HB2. So that means, since the left and right cosets are equal to each other, we should be able to say, aha, H times B2 should be equal to B2 times H. Right? The fact that these two cosets are the same, B2 times thing in H has to give us things in H times B2. That means little h times little b2 should really be equal to little b2 times h. Make you look skeptical.
Well, don't you need like a double hat or something like that? Like, does it have to be the same H?
Oh my gosh, it doesn't. Oh, you can wear two hats. I've worn two hats before. It feels weird, but I've done it. So unfortunately, the fact that this element is in here tells us that any B2H in B2H must equal H hat times B2 for some H hat in H. Doesn't have to be the same element in H. Just because these two cosets are equal, we've seen examples before that tell us these don't necessarily have to be equal element-wise. It's just that B2 times something in H has to give us something in H, something else potentially in H, times B2. And so we can rewrite little h times B2 as having to be equal to B2 times something in H, which we can't use H, we can't use H prime, we can't use H hat. I'm going with H double hat. Was that line?
I was thinking H bar, but
Nonsense, I like hats.
I like hats better.
I usually
It fits with my pun. It fits with my joke better of hold on to your hats at the start of this. Anyway, let's keep going. So now I'm going to use some associativity and write this in the form A2B2 times H double hat, H prime, H single hat. So what do we know about this lovely looking element? H double hat times H prime times H hat. Where does that thing have to live? Becca, Steph, any thoughts?
Never.
Don't be ridiculous, you've had plenty of cool thoughts. I'll give you a hint. H double hat is an element in H. H prime is an element in H. H hat. Here's H hat as an element in H. H prime is an element in H. If we take three things in H and multiply them together, where should we end up?
H.
There we go. Since these are all elements in H, and we're multiplying them all together, and since H is a subgroup, meaning H has to have closure, the product of all three of these things has to be an element in H. Whew. So we've shown that we can take any element in A1B1 times big H. If we take any element in this thing, it has to also be in A2B2H. And thus, A1B1H has to be a subset of A2B2H. Because we took an arbitrary element here, showed it had to be an element here, and doing so did require that we use the fact that H is a normal subgroup. If H isn't a normal subgroup, we wouldn't have been able to make this switcheroo right here and said, oh, H times B2 has to be equal to B2 times something else in H. Any questions about that? So that shows us that the first set is a subset of the second. We also need to show that the second is a subset of the first. Anyone want to see that? Really? You don't want to see me do an argument that involves 3 H triple hat, H quadruple, H quintuple, and H hextuple hat? Good, I don't either. Yeah, basically the same argument. By a symmetric argument, you can show the second one has to be a subset of the first, and thus they're equal. Let's write that down over here. You say, by a similar argument, A2B2H is also going to be a subset of A1B1H. Hence, these two sets are in fact equal. And we're done. We've shown that the issue we had with that one example in S4, where we tried to take a non-normal subgroup and found that our multiplication operation was not well defined, we've shown that that same scenario can't happen if H is a normal subgroup. We've shown that if you can take the same A coset and write it in two ways, and the same B coset written in two ways, no matter which order you take the product in, you're always going to end up with the same result. That one's a fun proof because it has so many H, because it has so many hats. Any questions or comments about what we just showed? So in general, here's the takeaway. If H is a normal subgroup, G mod H does form a group. If H is not a normal subgroup, bad things will happen that will cause the operation, this operation here, to not be well defined. Because we need H as a normal subgroup in order to be able to pull this switcheroo and say H times B2 has to be able to be written in the form B2 times something H, which was a necessary part of our argument. Right, let's look at another example of a quotient. So, well, remember our good friend Z mod NC, the cyclic group of order n? Remember how I told you, like a month and a half ago, that the elements of that group are just made up of the integers from 0 to n minus 1? That was our cyclic group of order n, kind of the standard go-to example of cyclic groups we've worked with all semester. What if I told you that was a lie? That's not what the elements in Z mod NZ are at all. So Z mod NZ, you may have noticed I'm using the same word mod and talking about G mod H. Z mod NZ is actually a quotient group. I just didn't tell you about it ahead of time, because I didn't want to confuse you early on. So let's look at the real Z mod NZ this time, where we know now that the elements in Z mod NZ are not actually integers from 0 to n minus 1. They're actually cosets of the integers. So, turns out this notation, hey, look, it's the same group slash subgroup of group that we have in looking at G mod H in general. So let's take a look at this. So in this case, our group that really is the integers. Our subgroup H of Z is going to be NZ. H is going to be a normal subgroup of G. How do I know H is going to be a normal subgroup of G, regardless of what n is? Okay?
Because multiplication does that?
Because multiplication waves back and forth?
It commutes, so the left coset's going to be the same as the right coset.
Yeah. Fun fact, in any abelian group, like the integers for instance, where the group operation works both ways, every subgroup is automatically going to be a normal subgroup. Because if you take A times H, you're just going to get elements of the form AH, where H is an element in H. Well, that's precisely just going to be elements of the form HA, since the order in which you multiply things doesn't matter in an abelian group, which is precisely the same as the right coset. So, in any abelian group, every subgroup is normal. So if you're looking at an abelian group, you're never going to have this sort of bananas thing like what happened in S4 at the start of class. If we're in an abelian group, then Nick's objections don't apply because we can just say, oh, little h times b2. Yeah, of course, that's just little b2 times little h for the same little h. For not in abelian groups, we can't necessarily say it's the same h. In an abelian group, we totally can. And so we don't have to worry about, is NZ a normal subgroup of Z? Yeah, because everything contains. All right. Let's look at our cosets. Because technically, our cosets of NZ and the integers are going to be the elements now in our quotient group Z mod NZ. So what would be an example of a coset of NZ? Hint, what's the identity element going to be? Right?
NZ.
Yeah, NZ itself is going to be a coset. And technically, instead of just saying NZ, I'm going to say 0 plus NZ, which by definition is just going to be elements of the form 0, plus or minus n, plus or minus 2n, etc., etc. Anything that's a multiple of n, if we take that set of elements and we're going to get nz, that's going to give us a coset of nz. It's just nz itself. Here's another coset. I'm going to take 1 plus nz, which I'm going to define to be elements that are 1 greater than a multiple of n. This will have 1 plus or minus n, 1 plus or minus 2n, 1 plus or minus 3n, etc., etc. And that's going to give us another coset, where we take everything in nz and we multiply on the left by 1. Technically, when I say multiply on the left, I mean do the group operation. We'll take things in nz and add 1 to them on the left, which in this case just means you take something that's multiple of n, you add 1 to it. And that's going to be one of our cosets. What's another coset going to be? Someone other than Elaine and Nick.
So would this go with like n minus 1 plus n?
And our last example, our next example is going to be things that are multiples of n plus 2. So we get 2, 2 plus or minus n, 2 plus or minus 2n, etc. And what is your claim our last one is going to be?
N minus 1 plus.
N minus 1 plus nz? Well, that would give us what? N minus 1, n minus 1, plus or minus n, n minus 1 plus or minus 2n, etc., etc. Why are you saying that's the last one?
Well, because once you go back to n, it would just be the first coset again.
If we were to take n plus nz, so that would be what? N plus or minus n plus or minus 2n, etc., etc. You're claiming that's a repeat?
Yes.
Which one?
What?
Which of these is that equal to?
It's equal to the first one.
Yeah, because these are just going to be multiples of n. This will also just happen to give us multiples of n. So here is our distinct cosets. Here are the actual elements of Z mod NZ. They're not the integers from 0 to n minus 1. they're the cosets corresponding to the integers from 0 up to n minus 1. Well, that's a good observation, Peter. What did you notice that? That after n minus 1, we start repeating itself. So here, so in actuality, z mod nz is going to be equal to these cosets. 0 plus nz, 1 plus nz, 2 plus nz, all the way up to n minus 1 plus nz. Because as Peter pointed out, once you start taking coset representatives past n minus 1, you're just going to loop back around. So n plus nz will be equal to this, n plus 1 plus nz will just be equal to 1 plus nz, n plus 2 plus nz will just be equal to 2 plus nz, etc. So we don't need to include elements past the n minus first. Oftentimes, just for shorthand notation, it's because writing this out is cumbersome every time. Instead of writing 0 plus nz, we'll write out 0 bar. Instead of writing out 1 plus nz, we'll write out 1 bar, 2 bar, etc., all the way up to n minus 1 bar. Which, if you do that, you'll end up with just 0 bar, 1 bar, 2 bar, up to n minus 1 bar. Where something to keep in mind is that when you put a bar over 0, 1, 2, etc., all the way up to n minus 1, we're no longer just talking about the single integers. Each of these is an entire infinite set of integers. So k bar in general is going to be the set of all integers equal to k mod n. In other words, 2 bar is all the integers that, for instance, if you were to, that are 2 greater than some multiple of n. And being 2 greater than a multiple of n just means you're going to be equal to 2 mod n. Here are your real elements in z mod nz. It's sets of all integers equal to k mod n for some k. For k ranges from 0 to n minus 1. Just a quick example. Let's look at z mod 6e. Let's see, how do I want to do this? From k equals 0 to k equals 5, 39 is going to be in which value of k bar? In other words, what's 39 mod 6 going to be equal to? 36 is a multiple of 6, and 3 greater than that will give us 39. I agree. So 39 is actually going to be an element of 3 bar, since 39 mod 6 is going to be equal to 3. In other words, 39 is 3 greater than a multiple of 6. And on the other hand, if we were to take something like, I don't know, let's get feisty. Negative 2. What's negative 2 mod 6 going to be equal to? Oh my goodness, Dr. Gerstle, you're giving us a negative number mod 6. Can you even do that? Sure. Negative 2 is basically how much greater than some multiple of 6. Indeed, because negative 2 is equal to negative 6, which is a multiple of 6, plus 4. Since negative 2 mod 6 is equal to 4. So in general, every integer that you might want to take is going to be in exactly one of these in cosets, from 0 bar to n minus 1 bar. And that includes both positive integers and negative integers. You just have to take your number k mod n, and then whatever that pops out to, it's going to be in that value k bar. Questions, comments, concerns? All right, have a good day, everybody. When we come back on Friday, we've got one more theorem in this packet. It's a fun one. It gives us a way of looking at G mod the center of G. And after we do that, we're going to go to our final packet on group theory, which is going to be about the next big theorem of the semester, the first isomorphism theorem, or FIT for short. And that well-defined issue, pesky coset, well-defined issue from today's class is going to pop up again. Have a good day, everybody. Why is my screen black?